In this lecture, we look at Sho Dynamics. Specifically, this lecture is for Physics AB. What we're going to do is we're going to apply F equals ma to a situation involving a horizontal oscillation. The oscillation itself occurs on a flat, frictionless surface. Okay, so we're taking a look at Sho Dynamics. Okay, here's a mass attached to a spring, mass M, spring constant K. Let's say that right here is the equilibrium position, right here is the displacement x from equilibrium. Recall that the spring force acts back towards the equilibrium position, and its magnitude is described by Hooke's law, K times x. Like so. Where, if you recall, of course, K is the spring constant, a measurement of the stiffness of the spring. Now, when we apply F equals ma to such a situation, we only have one force to worry about, and that's the spring force. There's no friction, and this is occurring on a horizontal surface, so the normal force and the weight cancel each other out. So then, therefore, we just simply have the following. Let's go ahead and apply F equals ma. Okay, so we have the spring force is equal to mass times acceleration, like so. Now, this expression looks deceptively simple, but it's not. And the reason for that is because this is not an algebraic equation. Instead, it is what is called a differential equation. And the reason for that is because as the displacement x is continuously changing, the acceleration a is continuously changing. The only way to solve a differential equation is by using the methods of calculus. So, this is not an algebraic expression or an algebraic equation. Instead, it's a differential equation. And the methods of calculus are necessary to solve this differential equation. This requires calculus. Now, of course, this is an algebra-based course. So how do we go about solving this differential equation? Well, I'm going to kind of do so in a roundabout way. Instead of examining F equals ma, let's examine the situation involving conservation of energy instead. And then once we do, I'll kind of circle back, if you will, to this description here of F equals ma and give you a basic understanding as to how it works. So let's approach the problem now in the context of conservation of energy, and I have it phrased in the form of a question. Copy the problem down in your notes. It says, show that the angular frequency of an SHO, omega, is equal to the square root of k over m. We now have a new expression here. Let's show the following. Okay, we're going to do so, however, in the context of conservation of energy. What we'll do is we'll take a look at two specific points in the oscillation. And keep in mind that at both of these positions, the energy has to be the same value. It's a conserved quantity. The first thing that we look at is the amplitude positions. At the amplitude position, the speed at that instant is equal to 0, and then therefore all of the energy E is potential energy. And then we'll take a look at a second arbitrary point in the oscillation where the energy is a combination of kinetic and potential energy. The total amount of energy in each situation must be the same because the energy is conserved. Okay, now let's just take a look at two simple pictures to get us started. Okay, so for this first picture, let's say that we're at specifically the amplitude position, like so. So at the amplitude position at that instant, the speed v is equal to 0. Therefore, I can write the total energy E in the following way. The total energy E is kinetic plus potential. The kinetic energy is 0, and then therefore the potential energy, 1/2 kx squared, is equal to 1/2 ka squared because we're at the amplitude position. This simplifies to become the following. Okay, and now let's take a look at an arbitrary point in the oscillation. Let's call this situation 2. So let's say that right here is the equilibrium position once again, and we have some arbitrary value of x. And then at that instant, the oscillator is either moving in this direction or in this direction with some speed v. Therefore, the total energy E here is a combination of the two forms of energy, kinetic energy and potential energy. So the energy here kinetic plus potential, is 1/2 mv squared plus 1/2 kx squared. And now, because the energy is conserved, this quantity here has to equal this quantity here. Let's see if it is. In order for me to do so, what I'm going to plug into this expression are our kinematics equations. Our kinematics equations that describe position and velocity. So recall from earlier lectures the following. Recall that the position as a function of time is this expression. We're going to ignore phase shifts, by the way, at this point. Phase shifts are just an unimportant mathematical detail. And then velocity as a function of time, which is this expression here. Let's go ahead and plug these expressions into here and here, and then let's just see what happens. So now I have 1/2 mv squared plus 1/2 kx squared. So in the first term for v, let's plug this in and square it. So I'm going to have right here 1/2 m, and then times this squared. So the negative sign squares out, and then a squared, omega squared, sine squared, omega t. Okay, then I have my next term, plus 1/2 k times x squared, where we're going to take this for x and plug it in and square it. So then a squared cosine squared omega t, like so. Do you see a trig identity here? Specifically sine squared plus cosine squared, which is equal to 1, if you recall from basic trigonometry. Notice, however, that I can't quite use that trig identity here yet, however. And the reason for that is because these coefficients here in front of the sine squared are not quite the same thing as these coefficients here in front of the cosine squared. So what do? Well, now let's take a look at this new value for omega. Omega is equal to the square root of k over m. What I'm going to do is plug that into here. Now let's see what happens when I do. Okay, so this quantity here then therefore is equal to the following. First of all, 1/2 m, a squared, and then times omega squared. So square this and the radical sign goes away, like so. And then I have the other term over here, like so. And now notice in the first term that the m's cancel out here and here, and now I have the following coefficients, 1/2 ka squared and 1/2 ka squared. So I can factor them out. Like so. And then right there in parentheses is the trig identity, which is equal to 1. So then therefore the total energy E is in fact 1/2 ka squared. Once again, this quantity here has to equal this quantity here because the energy is conserved. The only way in which that happens is if the following occurs. The angular frequency is equal to the square root of k over m. Here's how that expression shows up in F equals ma in the differential equation itself. Okay, now I'm not going to solve the differential equation for us because, as I said earlier, after all, this is an algebra-based course, not a calculus course. But here's where this expression appears in F equals ma. Take the mass m and move it down to the denominator on the right-hand side of the expression, and you then obtain the following. Constants multiplied by the position is equal to the acceleration. This is the differential equation for simple harmonic motion. The square root of the constants that appears in front of the position is the angular frequency omega. Like so. Okay, now this is, as I've said, kind of a roundabout way of showing why this expression has to work the way it does. Basically what I'm doing here is I'm dancing around a lot of calculus. But now let me actually demonstrate this equation to you. I'm going to demonstrate this equation to you by using some masses attached to springs. But when I do, it's a little bit easier to picture the expression, not in terms of the angular frequency omega, but instead in terms of the period, capital T. Okay, now the period is 2 pi divided by omega. So let's go ahead and take this new expression for omega and put it into the denominator here. When we do, we end up with this expression here. So the period of the oscillation depends upon two things. It depends upon the mass of the object m and the spring constant k. So let me now go ahead and demonstrate this expression to you by manipulating a couple of different variables. Okay, now in order to do so, however, I'm going to have to move my phone, so bear with me as I do. Okay, so let me tilt the phone like so. And then we're going to have a mass attached to a spring hanging from my attachment there. Okay, so now let me go ahead and manipulate a couple of these variables. Okay, the first variable that I'm going to manipulate is the mass m. So I'm going to start with this loose spring like so, attach it like this. Okay, and then right here is a small amount of mass. So if the mass is small, and it appears in the numerator of the expression for the period, this then means that the period is small. The time necessary for one oscillation to occur is a small number. Now the reciprocal of the period, if you recall, is the frequency. So then therefore, if the period is small, the frequency is high. A number of oscillations are made per second. So let me now go ahead and attach this little mass here to the spring like so, and then set it into oscillation like this. Let me make that a little straighter. Close enough, like so. And now we could, if we wanted to, for example, measure the time necessary for one oscillation to occur, that is with a stopwatch, and we would then therefore measure the period. The period would be a small number here, obviously, because ultimately the mass is small. Okay, now what I'm going to do is keep the same spring as before, this guy here, but now I'm going to switch masses. I'm going to use now this much larger mass like so. So then therefore, if the mass is large, then the period is large. The time necessary for one oscillation to occur is going to be a large number. This then means that the frequency, the reciprocal of the period, is a small number. Okay, now let me carefully attach this like so. Definitely have to be a little bit careful with this really loose spring. There we go. And now let me go ahead and set this into oscillation, for example, like this. And then with a stopwatch, for example, we can measure the period, the time necessary for one oscillation to occur, and we would measure a large number. So if the mass is large, the period is large, therefore the frequency is small. Okay, next what I'm going to do is I'm going to manipulate the spring constant K. I'm going to use the same mass for both of these demonstrations, but now I'm going to switch springs. So now let's think of the period not in terms of the mass m, but in terms of the spring constant k. This right here that I'm using right now is a really loose spring. In other words, the spring constant is small. If the number k is a small number and it appears in the denominator of the expression, then the period is a large number. So once again, the time necessary for one oscillation to occur is large. Okay, now let me switch springs. I'm going to use the same mass, but now I'm going to use this much stiffer spring. So this much stiffer spring has a big spring constant. So if the spring constant k is big, then the period is a small number. The frequency will be high. The period being a small number means that the oscillations will occur quickly. So let me go ahead and attach this like so, and now set this into oscillation, for example, like so. And you can see that the period here in this case is much smaller than it was earlier for the much looser spring. So for the dynamics of simple harmonic motion, the two most important numbers are the mass m and the spring constant k. Okay, now let me switch back to my big demonstration mass and spring, that is these guys like so. And now re-examine the equation for the period. Notice what the period does not depend upon. It does not depend upon the amplitude. So for example, let me set this into oscillation with a small amplitude oscillation. When I do, the amount of energy is small. In other words, 1/2 Ka squared is a small number. But let's say, for example, that right here I use a stopwatch and I measure the time necessary for one oscillation to occur. And now what I'm going to do is I'm going to make the amplitude larger. When I do, the energy is larger. But if I then measure the time necessary for one oscillation to occur, if I measure the period here, it would be exactly the same as the time necessary for the period here. The amplitude itself is not important. The reason why this discovery, when it was first made in the late 17th century, is so important is that it led immediately to the construction of the first accurate mechanical clocks. The reason why is because all clocks, regardless of their design, incorporate into their design an oscillation. An oscillator can be used as a timing element. And then the period of the oscillation itself has nothing to do with the amplitude. Now, this is not just the case for a simple harmonic oscillator, but it's also the case for realistic situations, which are called damped harmonic oscillators. There's actually no such thing as a simple harmonic oscillator. And the reason for that is because as the spring itself stretches and compresses, it loses energy as heat. This then results in the amplitude decreasing as a function of time. This is referred to as a damped harmonic oscillator. That is a realistic situation. There is no such thing as a simple harmonic oscillator. We'll examine damped harmonic motion a little bit later on in this unit. But for example, if I set this into oscillation like so, and I give it a fair amount of energy when I do, let's say that I measure the time necessary for one oscillation to occur, I measure the period. And then I wait a couple of minutes. In a couple of minutes, you're going to see that the amplitude of the motion here is decreased, and then therefore I measure the period once again with a stopwatch. It's exactly the same as it was earlier in the case earlier where the amplitude was larger. So for a realistic situation involving a DHO, a damped harmonic oscillator, the period does not depend upon the amplitude. Therefore, we can turn this into a clock. Now, the level of precision of your clock depends upon the period itself. So for example, let's say that the period here of the oscillation is 1 second for the sake of argument. Therefore, I could use this as a clock to keep track of time within a level of precision of 1 second. The period of the oscillation tells you the precision of your clock. Compare this, say, to an electronic clock that you plug into an ordinary electrical socket. The oscillation itself is the alternating current. The alternating current has a frequency of 60 hertz. The period is 1/60th of a second. Therefore, with an electronic clock that is plugged into an ordinary electrical socket, it can measure time to within a level of precision of 1/60th of a second. Does that sound familiar? It should. It's the same level of precision, of course, as our spark timers that we use in various spark timer experiments. The reason why the period that we can use of the spark timer is 1/60th of a second is because that's the period of the alternating current. The alternating current can be thought of as an oscillator. The most accurate clocks of all are what are called atomic clocks. What's actually oscillating in an atomic clock is not the atoms themselves, but it's actually electrons. Electrons that are transiting between various energy levels, and they do so in simple harmonic motion. The period of that simple harmonic motion is in terms of billionths of a second. That's extremely accurate. We actually no longer base the second on the rotation of the Earth. Instead, the second is based upon the transition of a specific energy level of electrons and a specific isotope of some atom that is being used as an atomic clock at a place in Colorado Springs, Colorado, called the National Bureau of Standards. At that location in Colorado Springs, we actually have an atomic clock that's used as the official clock of the United States. And then other countries around the world have their own atomic clocks that they use to keep track of time. And then, of course, we talk back and forth such that everybody's atomic clocks are all synchronized with each other. And then, therefore, everybody is using the same time worldwide. We actually have to correct for the imperfections, if you will, in the rotation of the Earth periodically. The Earth actually wobbles a little bit as it rotates. That has to be corrected for. It's corrected for ultimately, usually at the end of the calendar year, like when a fraction of a second is taken off of the year or a fraction of a second is added to it, such that all of the atomic clocks remain in sync with one another. So the importance of this discovery of harmonic motion, that the period of the motion does not depend upon the amplitude. It was first made in the late 17th century, and it led immediately to the construction of the very first accurate clocks. Let me just briefly write this down on the board for you. Okay, so let me tilt my phone back. There we go, like so. Okay, and now let's note the following. Okay, let's note that the period does not depend upon the amplitude A. Therefore, an oscillator can be used as a timing element. This led immediately to constructions of the first accurate clocks. This discovery immediately led to the construction of the first accurate clocks. Okay, so that's our look at Sho Dynamics. Yes, I have to dance around the necessary calculus in this lecture for this algebra-based course, but ultimately we used conservation of energy to show algebraically why this expression has to work the way it does.